aren't you good? Then I guess it's not a good day.
I don't know if I did a quiz, it would seriously be like, what's your name?
Really?
Yeah.
What's today's date? I might get that wrong.
I might not know how to grade that. I'm going to have to write an answer key. That could challenge me.
So I have the current date on my watch. I can't be trusted to remember.
So if I said it, my name is like Xenord or something like
Yeah,
that.
you might not get it. Well, if you tell me that's your name, that's your name.
Well, you just give
Well, there'll be
Xenord
new entry in the
credit.
grade book for Xenor.
Yeah. So how do you remember to wear your watch?
I don't take it on.
Okay.
This is currently fixed to the list.
It's like maybe last
It's
Thursday.
there from yesterday.
What?
It's there from yesterday, and I have no memory.
Pretty much.
Yeah.
It's good for like
We
middle
can-
of the night. I don't have glasses on.
We can
I wanna
prove
see
it
the-
at the induction. It was there.
That's
the
right.
day.
So it'll be
It
there
was
on
there
any given
yesterday.
day.
It'll be there today.
Now, telling time with an uncountable system of numbers would be interesting.
Oh no.
Okay, very Xeno's dichotomy there.
Yeah, that's a question I actually am intensely interested in, but that's another discussion. All right, so we were talking about trees.
About the homework, I did not quite understand the first question. How do you want to write?
What's the question say?
Construct a binary search tree in alphabetical order following data in the indicated order D, W, B, E, G, F, C, H, D, Q, A.
Okay, thank you. So what don't you...
So just draw the tree? Or?
Yeah.
Ah, okay.
So for example, if you have data coming in 7, 1, 2, 4, 3, 6, right? So the first piece of data that arrives is a 7, that's got to be the root of the tree. There's nowhere else it can go. The next number is a 1. It can't be the root because the root's already occupied. Does it go to the left or the right? Well, 1 is smaller than 7, so you move to the left. There's nothing there. That's where your 1 goes. A 2 is smaller than 7, so it'll go to the left. It's bigger than 1, so it'll go to the right. 4 comes to the left of 7, right of 1, right of 2, there's a 4. A 3 comes to the left of 7, right of 1, right of 2, but left of 4, so there's a 3. This is not very tree-like. 6 is smaller than 7, bigger than 2, bigger than 4, so there's where your 6 goes.
Okay.
So if I was building a tree from the data coming in that order, that would be what my tree looked like.
Incredibly.
So that's the first part of the question.
Easily efficient.
Yay.
And then show the tree and end and post order traversal of the tree.
Yeah, so
just
for this
rewrite
tree
it.
that you built, do a pre-order, in order, and post
So
order.
just rewrite the output.
Yeah,
Okay.
and your in-order one should be alphabetized, if you did the tree correctly. That's what the in-order gives us.
Isn't the in order already supposed to be alphabetized already? That is just simply the nodes arranged in alphabetical order.
Correct. Yeah, so if I traverse this tree in order, I should get 1, 2, 3, 4, 6, 7. If I don't, then I either built the tree incorrectly or I traversed it incorrectly. I don't know why we have white out on the podium. Someone knows I make mistakes all the time.
Let's just erase things on the screen.
Hopefully not on the whiteboard. Other questions? So I think we finished, I was talking about decision trees and this idea that we can use, say, a binary tree to do things like 20 questions. Right, so there's our super intelligent classification system that identifies unknown objects with just 2 questions. And you can extend it and so on. In the 80s was one of the resurgences of AI, and one big piece of that resurgence was expert systems. And people were convinced that they could create expert systems with computers that would do things like replace doctors and teachers and all sorts of stuff. And this was a lot of what was going on. So, are you feeling well? Yes. Leave. No. Do you have a sore throat? Yes or no. Are you sneezing? Do you have a fever? And eventually it would tell you you've got this condition. And you can approximate this somewhat, but it turns out that creating this structure is not all that easy. So you would go and you'd interview an expert and you'd ask them pointed questions and you'd build up a knowledge tree based on the interview that you had with them, and you try to capture this behavior. And of course, you can get, some percentage of the way there, but the stuff that is not something that the doctor has encountered before, that's where this sort of falls apart, right? So if you've never seen anything that wasn't alive other than a rock, and you don't ask the expert about that, then this is just going to say it's not alive, it's a rock. And until you've encountered whiteboard markers, it's never going to say, I think it's a whiteboard marker.
And then suddenly you end up with WebMD.
Yeah.
Fantastic for
Everything's
Yeah.
cancer.
All right, so I'm going to finish talking about trees shortly. So here's a sample tree. It doesn't have to be binary. We know we can traverse this in order, pre-order, post-order. So in order traversal, left node right, would basically move all the way down here until it found a 0, and then it would visit the root, and then it would come down to the right child. And that would be this traversal of the left subtree. It would visit the root, and then it would do the same thing on this tree. So move down, visit the 5, 6, and then traverse this subtree, 7, 8, 12, and we get, I'll swap these around because I didn't make it a binary search tree.
That's where you started.
Yeah, so I'll make that one a 3. All right, so now we've got a binary search tree. We can also characterize this kind of traversal as depth first. We're starting at the root and we're moving deeper and deeper and deeper into the tree until we hit a leaf, and then we backed up just one spot and we started going down again. So when we were traversing on this right branch, we moved down, we moved down, we moved down. We popped up one level and we started moving deep again until we got to the 7. And then we popped up one level and we started moving deep again. It's concentrating on trying to explore the deepest parts of the tree first. And that's what we get with a left node right, a node left right, and so on. But there's an alternative, which is breadth first, where instead of trying to go deep, we try to go across and visit nodes at a small depth completely before we move to a deeper level. And in a breadth-first traversal, we might pick off something like the root node, which is 4, and then come down to the second level and pick off 2 and 6, and then come down to a slightly deeper level and pick out our 0, 3, 5, 8, and then come down to the next level and pick out 7 and 12, and there's nothing any deeper than that. And we don't get a sorted list, but it's a different way of visiting all the nodes in this tree. And these correspond to different things that we might want to be doing that are coded as a binary tree. For example, when you're running a maze, I don't have my laptop booted. I'm really horrible at creating mazes on the fly. Alright, so you get the idea. We're going to start here, we're going to try to get here. Each time that we come to a possible decision point, we say, okay, let's go off to the right and see where that takes us. And if that doesn't give us an answer, we come back to the last decision point that we made and we try a different path. Okay, that's typically a depth-first strategy. We start off at the entrance and we make a set of decisions and we go until we hit a dead end or we find the answer. If we hit a dead end right here, we back up and we go to the previous decision point and we make a different decision. So we're moving down as far as we can, and when we dead end, we just hop up one level and we come down and we make another decision. Okay, so typically maze running is depth first, but we could do it breadth first as well. We could come down here and we could follow a series of paths, and if we dead end, we could go back to the first branch that we made and go in a different direction. And if that dead ended, we could find a different direction for that. And we could approach this thing from a breadth-first strategy. And we'll explore those in detail in discussions on data structures. But to implement a depth-first search, we need to use basically a stack. So this idea of pushing things on the top of a stack, pulling them off from the top of a stack. Okay, so I think you touched on this in 121. The analogy I use is when you go into a buffet and there's a stack of plates, right? You can take the top plate off, or you can put a plate on top. You can't get to a plate that's not on top, though. If you want the plate that's 3 down, you've got to pull the top 2 plates off, and then you can get to the 3rd plate. That's a stack. And the last plate that was put on the top, that's the first one that's going to be taken off. So to traverse this thing using a stack, and I'm going to draw my stack in this direction, so this is the top of stack. I'm going to take my root node, I'm going to put that on the top of the stack. I'm going to come down to the left, I'm going to place a 2 on top of the stack, so now that's the top of the stack. I'm going to come down to the left and place a 0, that's the top of the stack. And I have nothing left that I can visit from the 0. So now I'm going to remove the 0, that's going to be the first node I visit. And now my node on the top of the stack is 2, I'm going to visit its right child. That'll give me a 3, which becomes, left node right. So I'll visit my 2, and then I'll visit its children, which will be a 3. Now if 3 had children, I would push 3 on there, and I'd push its children onto the stack. And when I run out of nodes, I would pop off the top of the stack, and that would be the next node I would visit. And this depth-first search has a natural stack-like structure, which is why it links to recursion, because recursion is basically using a stack. That's how the CPU and the operating system are keeping track of your calls, is by using this stack-like structure. The last call that you did is the first one that you'll return from when you say return. Breadth first uses a queue, which is a different kind of structure. A queue, you push things in the beginning, 1, 2, 3, 4, 5, and the first thing that you remove was the first thing that you pushed in. So a queue is like a line at the grocery store. You have 10 people in line. The first person in line is the first person who's going to be helped. The second person in line will be the second person helped. If somebody new comes along, they go in the back of the queue, and they'll be helped after everybody who's already in there has been helped. Question or stretch?
Question.
Okay.
It's sort of a half-formed thought, but I know that there's a maximum limit of function calls you can make.
Mm-hmm.
That's probably the primary limit to recursion.
Correct.
Besides the
Besides
efficiency. But could you use this stack structure, like implement it manually in an array or something to sort of emulate recursion, but
Absolutely.
not actually do recursion to
Yep.
be more efficient?
Yeah,
Is
you can
that
do
just
this.
turning it into a normal algorithm at that point? Is that?
It's kind of semantic whether it's recursive at that point or not. But yeah, you can do this with a go-to statement in an array. But you know, you need subroutine calls. You can just record in this array where you are and values of local variables and so on, and go back up to the beginning and execute this again. And yes, you can do this in assembly language pretty easily. And you don't even need a call return structure. In fact, it's not a bad 270 assignment for future reference. Yeah, definitely. Like I say, I don't know if that would be considered recursive or not. I could probably still consider that recursive. Even though you're not calling it out using the stack.
So there's a pre, in, and post order for L and R, or is L and R just one that does?
LNR is in order, NLR is pre, LRN is post. It refers to where the N is, whether it's before, after, or in the middle.
So L and R in order.
Yeah, so LNR is in order. Left, right node is post order. And node left, right is pre-order.
And the other thing is that stack you mentioned there is explicitly called a first in, last out stack, right?
Stack is always a first in, last out, or a last in,
Because
first
it's
out.
called a stack, okay.
Yeah.
And,
And a queue is a first in, first out, FIFO.
okay.
So the two opposite concepts.
So they're two opposite concepts, yeah, or dual concepts maybe.
Did we learn about those in 222 or?
Yes. Yeah, we'll spend a fair amount of time on those. Hmm?
Everything goes to 220.
Everything goes to 222, yeah, that's where life begins. So yeah, we can do a breadth-first traversal with a queue. We start at the root, we put 4 into the queue, and then we simply remove the head of the queue, push all of its children into the back of the queue. So we remove the 4, which we've already visited, and we push its children, which are 2 and 6, onto the queue. Now we remove the head of the queue, which is our 2, and we push all of 2's children onto the queue, so there's a 0, 3. Remove the head of the queue is 6, push its children, which are 5 and 8. Remove the head of the queue, which is a 0, push its children, there are none. Remove the head 3, push its children, there are none. Remove the head of the queue 5, push its children, there are none. Remove the head of the queue 8, push its children, 7 and 12. Remove the head 7, no children to push. Remove the head 12, no children to push, queue is empty, we're done. That gives you a breadth first traversal. So queues, breadth first, stacks, depth first. More duals. All right, last comment on trees. Trees are, in some sense, a way to describe a search space. For example, do you know the n-queens problem? So, how many people here know how to play chess? Not necessarily well.
It's this one. It's this one.
Right, so chessboard. Eight by 8 board. Queen, most powerful piece on the board. A queen can move horizontally, vertically, or diagonally. And if there's anything in its way, it can capture it. Okay, including the king, which if you capture the king, you win. So this queen can move like that, it can move up and down, it can move along this diagonal, or it can move along this diagonal. So the question is, if you have an 8 by 8 board, can you place 8 queens on the board such that none of them capture any of the other queens?
Yeah,
And clearly they've got to go in different rows, because if you put another queen in this row, they could capture each other. And they've got to go in different columns, and you've got to stay off the diagonals of each other, otherwise you could capture. So how do you place 8 queens on an 8 by 8 board such that none of them capture each other?
I know that they cannot move like horses.
They don't move like horses, right?
Yeah, so
Yeah.
I can say that it is very explained, but I don't know how to explain it in this.
Yeah.
Well, place the first queen.
So place the first queen.
Okay. The next
And-
one would probably end up to and over one, I think.
Oh, okay.
So
Or
let's-
down to an over one, other one.
right? So
Yeah.
you could go like that.
And then repeat, and when you hit
Like
the bottom,
that.
sort of loop aroundish, and
Yeah.
there you go.
So I think that'll get you there.
Nope,
Did we hit a diagonal?
I think you hit a diagonal.
Yeah, so these two will capture.
Basically, if you the top left one,
So swap the
if
last
you just put that one down
Mm-hmm.
and do same thing, it should work.
Okay. So yeah, we can trial and error this and probably get to a solution.
I know it's solvable up to a certain number, and obviously we just proved it's solvable up to 7,
It's up to
I
8.
think, right?
I think so.
No, solve 7.
Can you just draw that?
No, the 7 is
That's
more.
okay. So how could we get a computer to solve this for us
Magic.
without using magic? So we can think of this as a tree. We can use a tree to describe the possibilities. So what we're going to do is we're going to label these 1, 2, 3, 4, 5, 6, 7, 8. Let me go on like this.
There's a number file video on this if anybody wants to
Cool.
look it up after.
So all we have to do is figure out which column we put the queen in for each of these rows. Because we know we're going to have a queen in each row. And we just need to say what column should this queen go in, what column should this queen go in, what column should this queen go in. Right? Well, there's exactly 8 possibilities for the first queen. Right? 1, 2, 3, 4, 5, 6, 7, 8. This is column 1.
Oh boy, it's factorial.
And when we place our first queen, there are 8 possibilities
What?
for where we can place the queen in column 2. Now most of these aren't going to be good possibilities, but we could place the second queen in any of these 8 columns. And if we placed our first queen in row 2, we could again place our second queen in any of 8 possibilities. And same with our third, fourth, and fifth, all the way up
Now
to
some
our
of
8.
those aren't usable options.
Yeah.
They're not usable, but they're options, right? Column 3, that's the third queen.
It's defining options in a little bit of an odd way.
You always have an option, you have free will.
Well, what's the point of
You
separating
can place the
them?
queens anywhere that you want.
So in column 2, you have 7 valid spots.
Perhaps. So ignore the goal of the game. Let's just look at how we can place 8 queens on a chessboard, 1 per row. That's what I'm enumerating here.
Okay.
And then
Okay.
after that, you trim out all the places you can.
And there are a lot of possibilities here.
Isn't 8 to 8?
It may be worse than that.
No, because you've got 8, you have 8 decisions with 8 outcomes.
Yeah.
Pretty sure it's 8 to the 8.
Yeah.
It's 8 times 8 times 8, so on.
Yeah, so I think it's 8 to the 8, right?
That's a big chunk of numbers.
I mean, unless, well, you did say 1 per row. If you remove that possibility.
Then there's a lot more. Yeah, then you're into factorials, I think. So just looking at this, the ways we can place queens in 1 queen per column. Sorry, these are rows. We can enumerate the space of possibilities using a tree. It's an 8-way tree, it's not a binary tree anymore. But each point on this tree represents a possibility. And so we could write a program that simply builds out this tree and explores each possible path and finds a path where nothing can capture anything else. So it could come down here and there's a queen in column 1 and there's a queen in row 2, column 1. And right away it knows that those queens can capture each other. So that's not a solution. It could come down 1 and 2 and some other path, and it would find that 1 and 2 means we have a queen here and here, and they can capture each other diagonally. Well, we can enumerate all the possibilities for where we can place these 8 queens using a big tree. And then we can traverse it to find different particular placements, and we can examine each of those placements and see if it is a solution to our original problem or not.
So we'd have to check to see if, we have to check each one individually.
You'd have to check each one individually.
Individually simplify the tree.
But we can simplify the tree. For example, right, each of these things, remember, they branch off horribly and have these huge numbers of subtrees after them.
Is that 8 to the 8 factorial?
I think it's just 8 to the 8.
Yeah.
But as soon as we come down this branch, we visit this first node and we say, okay, the first queen is going to go in column 1. And then we come down here, column 2, we're going to put a queen in column 1 there. And we see right away that those can capture each other. So what we can do is prune the tree. We can say we don't need to consider this possibility or any possibility that came off of that. And bam, all of this goes away.
You also don't need to consider that possibility anywhere. Once you pick place 1, anytime you see place 1, you can just drop that whole tree.
Well, we're not going to see place 1 anymore because we've just pruned that branch off.
But once you go down to 2, you're going to see 1 again right beneath it, aren't you?
Well, we'll see 2, 1, but we won't see 1, 1 again. Right? We'll never encounter this possibility again.
Oh, right, no.
Right.
Well, I mean, couldn't you get 1, 2, 1?
Yes,
But that's not 1, 1.
but that's not 1, 1. Well, we could get to 1, 2, and when we find that that's a conflict, we can prune 2, and we can prune all of the tree that comes off of that node. And the first one that may get us a little further is 1, 3. And we'll have to dig down further in this branch before we find a problem. But each time we find a problem, we can potentially hack out a bunch of the tree, so we don't end up actually exploring every possible path through here if we're smart about how we do it. So pruning is an interesting time-saving efficiency technique that we'll also talk about in data structures.
Uploading a lot of work onto yourself, aren't you?
Yeah.
Put it on your to-do list.
Well, that's why 215 goes along with the sequence, right? Because it's hopefully doing some setup for this stuff when we get to it and we start working at it from a programming algorithm perspective. So lots of problems yield themselves to this kind of approach. Another one is like finding subsets. You have a set of integers and you want to find a subset of those that add up to a certain number. How do you do that? And you can describe that as a tree, where you simply branch off for each possible number, and you can enumerate all the subsets with a set of trees. So,
What sort of tasks can you not describe with a tree?
I don't know.
I'm trying to think.
If all you know is trees, then everything ends up looking like a tree. But there's certainly a lot of things that aren't like naturally thought of
Actually,
as trees.
I used one to organize my daughter's Christmas wish list.
Oh, cool.
I went through just the first 20 to kind of like I said, okay, do you want this more on the next one, or this more on the next one after that? And just organized it like
Oh,
that.
cool. So it is a binary search tree. Nice. So you want to find a set of numbers from here that add up to 49, right? And we can break that out as a big search tree.
We're assuming that we can't use numbers twice.
Can't use numbers twice. So I could have 27, 24, 19, 14, 11, and 8. And if I include the number 27, I could also include any of the other 5 numbers. 24, 19, 14, 11, and 8. And if I have 24, I could include 19, 14, 11, 8. 19 could include 14, 11, 8. 14 could include 11 or 8. 11 could include 8. 14 includes 11 or 8. 11 includes 8. And you keep going. So 14, 11, 8, 11, 8, 8, and it's not too bad. 11, 8, 8, 11, 8. I think that's your whole tree off of 27.
This is basically blackjack.
Yeah,
You keep going until you bust, right? Like,
yeah. So you got to do the same thing under 24, 19, 14, 11, and 8, but they get smaller and smaller as you go. And every possible path from here to a leaf represents some subset, right? And you probably want nulls over here so that you don't have to go all the way down to an 8. So we could have a terminator for that.
So wouldn't it be easier if we were, because in this case, order does not matter, wouldn't it just be easier to say, are we including 20, as our choices of rule, are we including 27, yes or no, 24, yes or no? 19,
Yeah, so,
binary. Yeah.
right, you could enumerate, you could represent your subset with a binary string, and you could count in binary. But if you break it into a tree, it'll look something like this.
If you represent it as a binary string, it sounds almost like converting from binary to base 10.
Yeah, it's just using a weird variable base. An advantage of the tree-like approach, though, is if you order this stuff correctly. For example, once I start off at 24 and I add 19, start at 27 and add 24, my number is too big. Again, I can prune all of this. And start at 27, add 19, that's 46, and that's going to be too big right there, so I can prune that off. 11 will be too big, that'll be too big. And you can really quickly start dispensing with possible branches.
Yeah, blackjack.
Yeah.
Seems like in the process of dispensing possible, or removing possible branches, you really quickly find the answer.
Hopefully, except I think the answer comes off of here, I think.
Maybe not.
Maybe it's 24, yeah, I think it's 24, 14, and 11.
No. Oh, right.
Yeah, that
Sorry,
would be
sorry.
49.
Yeah.
And if there's no way to do it, you visit all your paths, and when you run out of options, you haven't found an answer, then you can say there's no answer. Yeah. All right, so those are trees, and we'll do a lot with trees and data structures. They pop up all over computer science. That's some examples of what trees look like. The other part of our subject is graphs. And a tree is an example of a graph. Trees are a subset of graphs, but graphs are a much bigger space.
And sometimes they're bigger.
I like how you managed to represent what a graph is in terminology that we just learned in this course.
All right, so mathematically, we think of a graph as a pair of sets, a set called V, vertices, and a set E called edges. So vertices E equals edges, and our set of vertices cannot be empty. An edge has one or two endpoints, which are vertices. So an edge has two or one endpoints associated with it. Those endpoints are themselves vertices. And we say the edge connects those endpoints. And we're mostly going to talk about simple graphs. A graph is simple if for any pair of vertices there's either one edge or zero edges connecting them. So here's an example of a graph. Three vertices, three edges.
But that one, wait, pair, okay.
Yeah. So that's a graph. This is also a graph, but it's no longer simple, because we've got two edges connecting those two vertices. So we won't worry about non-simple graphs for the most part. This graph has a loop. This graph does not have a loop.
They don't need one, though, right?
You don't need to have any loops, no. This is also a graph. Vertices and edges, each edge connects one or two endpoints, which are vertices.
A simple one?
It's still a simple one.
What about this?
This would not be simple.
Because the pair is that one in the corner and that one in the corner.
Right.
So a pair of points can be made.
Pair could be the same point choice.
And if you just had like a vertex or a vertex and one edge, would that be the graph as
It's
well?
got to be connected to another vertex somewhere. So
Okay,
we can't
one
just
or two
have an edge like that.
Looking at the back on that.
If it's not connected to another vertex, it's got to connect back to itself. It's got to have a
Oh.
vertex on each end, but it could be its own beginning and end.
Okay. Because I was wondering about each edge has one or two endpoints, which are vertices, but that's, so it just has to be connected at some point.
Yeah, so
Okay.
maybe I could say one or two distinct endpoints.
Okay.
All right. What are graphs good for? Pretty much everything, like even more than trees. Computer networks, telephone networks.
Decisions.
What?
Decisions.
Decisions. Describing a social network. Everybody that you know,
Did you say a graph or a simple graph?
a graph.
Okay, so a graph can also describe, a non-simple graph can also describe state machines,
Correct.
like at 250.
Yeah, so we could do state machines with this. Well, those would, yeah, okay, those might not be simple, because you might have two.
No, because you'd have another one going at.
Right, right. Yeah, so we could represent state diagrams with these. You can have things like, so Nick knows Izad, and Izad knows Carol, and maybe I've never met Carol, and Izad also knows Bob Knight, and I do know Carol, but let's say I don't know Bob Knight. All right, so there's a relationship graph describing these four people. And you can tell from this, for example, that I have a connection to Bob Knight through Izad. Right, so this is what LinkedIn and Facebook and all this stuff is doing under the hood.
The distance between you and Bob Knight is 2 then.
The distance between me and Bob Knight would be 2 in this case. Right? So you can do things like, you know the Oracle of Bacon?
Oh gosh.
Bacon's number, yeah.
Yeah. So Google Oracle of Bacon, you can put in any actor or actress's name, it'll connect it to Kevin Bacon in like 6 or fewer hops usually 2 or 3 hops. Like this person starred in this movie, which also had this person who starred in this movie with Kevin Bacon.
National Geographic actually did one with the entire world,
Oh, cool.
and they picked out 2 random people, or a set of random people or pairs,
Mm-hmm.
and said send this package from this person to this person, and I think they got it down in 8 tries.
Mm-hmm.
And it was just, and it's super weird. It's like, oh well, I know some.
Yeah.
For example, there was someone who was in Pennsylvania and had to send something
Right.
to this person in this remote village in Vietnam.
Yeah.
And figured out, oh well, I know this one person in, UCLA who works in the Asian languages department. And
Yeah.
It's like, oh well, I have family who knows someone in Vietnam.
Right.
It's like,
Yeah, most of us are several degrees of separation from anybody else. it's kind of crazy, but if you think about it, if you only know 10 people, and each of them knows 10 people, that connects you to 100 people through one level of indirection. And if each of them know 10 people you don't know, that connects you to 1,000 people. And after 9 hops, you're connected to 1 billion people.
Wouldn't it be after 2 hops you can get 110? Or after
Well, yeah.
1,000?
Closest order. And if you know 100 people, right, with 2 hops, you've got 10,000. With 3 hops, you've got 1 million. I mean, it grows really quickly. So you can represent that kind of stuff with graphs. Like I say, computer networks, the telephone system, all sorts of things can be represented using this idea of graphs. We can also have directed graphs. So we could add some direction over here. So Bob Knight has influence over Izad. Izad has influence over me. Izad has influence over Carol. And maybe Carol and I have equal influence over each other. So we can have a notion of direction.
Would that require a separate edge for each direction, or
Yes.
directional?
So in that case, an edge is given by an ordered pair UV. Where the pair UV corresponds to an edge from U to V.
Is that still a simple graph?
Technically, I'm not sure if it's directed. I think it's still simple
What if you
if they're in opposite directions. I'm not going to ask you like sneaky questions like
on
that.
a directed graph, could an edge have no direction?
I don't know. I think you have to have a direction. So we could represent roadways with directed graphs, right? So in some cities, all your roads are two-way. You can use an undirected graph. In Portland, everything's a one-way street. So you'd have a directed graph, and you could use that to navigate, right? You want to get from point A to point B, but you don't have an edge going from A to B, but you could find some other pathway, right? So mapping software, things like that, all this stuff is.
You can think of
sitting under the hood.
airports too.
Do what?
Airports and planes.
Yeah, airports and planes, same thing.
Good example of that.
And you might be able to fly from A to B, but not directly from B to A, for mysterious reasons that only the airline knows.
It's the algorithm, blame the algorithm.
Yeah. That's some serious computation there. You want to talk about like complex problems?
I mean, what, finding a path from point A to B over a couple nodes?
Dealing with
Oh,
air traffic.
Right, yeah.
So there's a thunderstorm coming into Newark, and your plane leaving Heathrow has to make adjustments because everything's connected to everything. It's like frightening.
Well, like, the other thing is like, when you're trying to travel cross country, you have to go way out of your way, and it doesn't make sense.
Yeah,
But there's some crazy reason that you have no idea why.
right.
But it's like when,
And it's like cheaper if you go like an extra 10,000 miles to get from here to like Seattle.
yeah. A lot of the time, like when I would fly down to California, I would go to Seattle first from PDX.
Yeah.
And it doesn't seem like it makes any sense,
Mm-hmm.
but there's some reason, I'm sure.
Yeah,
I'm just doing it for fun.
we can hope so.
It's all about the volume, the number of people they can carry. So if you only need
Yeah.
5 people to go up to get down to California from Portland, but you need 100 people to get to California from Seattle,
Right.
send them up to Seattle because it's a little bit closer, but then launch them all down there with the other.
Yeah, it would be cool if it was that logical. But it's not always.
Like the mysterious disappearing seats.
Mm-hmm. So we can make this arbitrarily mathematical sounding, but I'm not going to for now. two vertices U and V are adjacent if there's an edge connecting them. So I could say in a directed, graph G equals V comma E, two vertices, V1, V2, and E, et cetera, et cetera. But you get what I mean, right? So if there's an edge between these 2 points, we say these 2 points are adjacent. If there's an edge E connecting them. And in that case, we say E is incident to U. And we can also say E is incident to V. And we're going to use these notions to describe graphs in a way that a computer can grok. Probably tomorrow, because we just ran out of time 10 seconds ago. All right, so we'll talk a little more about the properties of graphs. We'll talk about neighborhoods. We'll give some examples of some types of graphs that we'll be playing with, and then we'll talk about how to start representing these things in the computer.
If you had like 4 vertices and 4 lines connecting them, and then you added like 2 to each side, that would be like a graph as we traditionally
Sure. Yeah.
do, right?
Sure.
Okay.
That's one graph.
With the vertices being the cells. Like, let me draw it.
Okay.
That would extend it forever.
Mm-hmm.
Would be the cells.
Cells.
The vertices would be the cells.
Which cells?
What?
Which cells? Yeah.
Well, that's what it looks like, but aren't the vertices what contain their data?
What kind of graph are we talking about?
Like, this kind of graph.
Yeah, but the cells aren't